All right, so tonight we're going to talk about a couple of things. We're going to talk about the difference between a polar bond and a polar molecule. We're going to talk about the difference between molecular geometry and electron domain geometry. And then lastly, we're going to talk about what resonance means and the cool things that it does / cool things that cause us to know that it's a thing. We're just going to start that again. All right, so tonight we're going to talk about three things. Reese's is currently headbutting my computer. We're going to talk about... all right, today we're going to talk about three things. We're going to talk about the difference between molecular shape and electron domain shape or geometry. We're going to talk about the difference between a polar bond and a polar molecule. And we're going to talk about this thing called resonance. So the first thing that I'm going to do, I'm going to run you through All right, so the first thing that I'm going to do is I'm going to run you through how to create the Lewis dot diagram for water. So this should be a good review from the previous videos. So we know the formula for water. We're going to take a guess at the geometry. We're going to count up our total electrons. We know we have 2 hydrogen atoms with 1 electron apiece. We have 1 oxygen atom with 6 valence electrons, which gives me a total of 8 electrons to work with. I've used up 4 in the bonds that I've drawn, leaving me with just 4. So if I was inexperienced, I might draw my Lewis dot diagram to look like this. If you've had class with me before, hopefully you're screaming at the computer. We know that a better way to represent my molecule is to shift my electrons to what appears to be in 2D space the top of the molecule. Hopefully, if you haven't learned about molecular geometry, you're saying, wait, Dubs, you said electrons like to be spread out the most. Well, the fact of the matter is this is the most spread out that they can be. So I'm going to switch over to a PhET website, and I'm going to post this for you guys on our website. It allows you to rotate in 3D space the molecule. So this is water, and you can see my molecular geometry is bent. Okay, I've got a molecule here that's bent. My electron geometry is tetrahedral. And if I pivot like, oh goodness, like this, hopefully you can kind of see that tetrahedral, right? We've got 4 electron domains attached to it. So this is one of the other reasons why I love the ABN formula so much. My central atom's A. I have 2 atoms bonded to it, and I have 2 non-bonding pairs bonded to it. Now if I go to a reference table, or hopefully you're starting to create that reference table in your brain, AB2N2 is here. I have 2 things bonded, 2 things non-bonded. That puts my electron domain geometry, which is all of those electron domains, which includes lone pairs and bonds. I have a tetrahedral molecule, but if I have just the atoms included in the big picture, I have a bent molecule. Either one is fair game. The AP test can ask you what the electron domain geometry is or what the molecular geometry is. So having an idea of both is really in your best interest. If you know electron domain geometries, it becomes a little bit easier. If you know them in 3D space, it becomes a little bit easier for you to see the molecular geometry in 3D space as well. So if I go back to this PhET simulator, I just kind of want to walk you through it in this video. So if you go home and play, you can. Down here, you'll see that you can kind of quiz yourself. So you could unplug these. You could look at a shape, manipulate the shape and say, okay, well, I have 4 things bonded to a central atom, and all 4 of them are atoms. So both my electron geometry and my molecular geometry are going to be tetrahedral. You click the boxes, you check your answers. You also have the ability to show your bond angles, which is also fair game on the AP test. So if something has 4 atoms attached to it, you're looking at roughly 109.5 degrees between each of them. The other thing you can do to help differentiate between the two shapes is remove the lone pairs. So now without the lone pairs, hopefully you can see that this is really a pyramid shape, right? These 3 are on a plane, the 3 white ones are on a plane, and the blue one is elevated, where that might not be as obvious tucking the lone pairs in there. So that's a very brief overview about the difference between electron domain geometry and molecular geometry. All right, so the next thing that I want to talk about is the difference between a polar bond and a polar molecule. So in class, I taught you previously, I taught you that if there's a large difference in electronegativities between the 2 atoms, you create a polar bond. So in this case, fluorine is extremely electronegative where hydrogen is not, which creates a partial dipole that's negative by fluorine and a partial dipole by hydrogen that's positive. So if I take this and I extend it to a more complicated molecule, something like CF4, you can trust me that this Lewis dot diagram is correct. If you don't want to trust me, I guess you could test your knowledge and make sure that you come up with the same answer that I do. Just as a heads up, you can also do lone pairs as straight lines like this. Obviously, you see it saves you some time, and it's a common enough notation that it would be acceptable in our class. I would recommend going to the dots on the AP test just for clarity's sake. So here I have 4 polar bonds. I have a partial negative charge on each of my fluorines because fluorine's more electronegative than carbon, and a partial positive charge on carbon. Now, if you're just looking at a piece of paper and you're not taking into consideration the whole molecule, it might be easy to say, well, the electrons aren't distributed evenly. Right here in this belt, there's more electron density than here in the center. But if you actually look at the whole molecule, again, this is where we'll have to use this one. This is where PhET can really come in handy. It's got some preset molecules. There's also an option where you can draw your own molecule, which is pretty legit. So we're going to work with CH4 and just pretend like the H's are F's. It'll result in the same dynamic conversation. So if each of these white balls is slightly electronegative, that partial negative charge is evenly distributed over the course of the whole atom. And if it's evenly distributed over the course of the whole atom, there's not one spot that's negative and one spot that's positive, right? That electron distribution is even. If I wanted this molecule to be polar or a similar molecule to be polar, I would have to change this piece here, or one of the pieces, it doesn't have to be this particular one, to something with a different electronegativity. Now, very clearly, I have an unequal distribution of electrons. There's way more electrons on this side of the molecule than there is here. So if I take a look at a pretty common molecule that is NH3, NH3 has 3 polar bonds, right? Each nitrogen-hydrogen bond is polar. But the really glaring thing is this lone pair here up at the top, right? That's going to create an extremely dense population of electrons that's not present down here. Here they're taken up in bonds, right? They're occupied in bonding. Here at the top of the molecule, they're not. Another way that this is represented is with like this kind of rainbow effect. Here, the red is showing your electron density. And in this picture, it's so obviously not distributed evenly around the molecule. Here, CH4, if we could flip it over, you'd see that it's uniform throughout the molecule. H2O, back to that first example, those 2 lone pairs at the top create an electron density here. And HF, our very original example, very clearly your fluorine is going to be more electronegative than your hydrogen. That molecule is going to be polar. So just because there's a polar bond in a molecule does not mean that entire molecule is going to be polar. The only way that you can be certain is to draw the Lewis dot diagram, translate that to a 3D model in your head, place the atoms appropriately on that 3D model, and see if the electrons are evenly distributed. That sounds slightly overwhelming, but with practice it becomes relatively simplistic. All right. So the last thing that I want to talk about today is resonance. If you were in my honors classes last year, you heard about it a little. I don't believe that I discussed it very much with my Chem 1 classes. And if you've come from outside of Page, I really have no idea what your background is. So for today's discussion, we're going to focus primarily on ozone. Ozone has a total of 18 valence electrons to work with, 6 for each of the oxygens. So we're going to create a molecule. I've just used up 4 electrons in my bonds, leaving me with 14 electrons to work with. I start on my outside molecules first, and I place those electrons in pairs. So I've got 2, 4, 6, 8, 10, 12, 14. So now I've used up my valence electrons. I have to see if using up those valence electrons satisfied the octet for each of the atoms in the molecule. If I focus here on this oxygen, I've got 2, 4, 6, 8. If I focus here on this oxygen, I have 2, 4, 6, 8. But if I focus here on the central oxygen, I have 2, 4, and 6. Not a stable octet. So I'm really left with 2 options. Well, one option. I need to move an electron pair from being a lone pair to being a double bond. And now all of my atoms are going to be satisfied. I have 2, 4, 6, 8 for this oxygen, 2, 4, 6, 8 for this oxygen, 2, 4, 6, 8 for this oxygen. Unfortunately, or fortunately, there's a secondary structure that's viable. That one, right? I'll highlight the bonds in another color. My bonds are now in green. So my blue lines are showing you the non-bonding pairs. The greens will be the bond. Then the question really becomes, which of those 2 models is correct? And the answer is neither. And this is not me being difficult. This is not scientists being difficult. We thought for the longest time, maybe not the longest time, we thought that perhaps these were both viable, and sometimes one happened, sometimes the other happened. One giant misconception is that resonance is actually somehow these 2 molecules switching in between one another. But the fact of the matter is when we went in and we developed techniques to be able to measure bond length, this bond length and this bond length should be different. Hopefully you recognize that a single bond is going to have a larger bond length than a double bond. Okay, so that means that this one should be longer and this one should be shorter. But when we measured them, we found that they're actually identical, which means that neither of these structures is appropriate. If we're going to draw the resonance structure for oxygen, the most correct Lewis dot diagram for oxygen, we need to have a partial bond on each of the oxygens, in between each of the oxygens, and then our lone pairs get kind of awkward because we can't really draw all of them because a partial bond is happening, etc. So the best way to write out resonance structures when resonance is an option is to draw both of your potentials and then to draw the hybrid version of them kind of in another step. And the way that they're most often represented is with this kind of double arrow to show that these things are creating that third thing. So the most common way to show resonance structures is to list these 3 structures out. And then actually in between this first structure and the second structure, you're going to do a double-headed arrow like that. That's showing that this and this are actually partner resonance structures. And the reason we can have this partial bond that should be somewhat not intuitive to you has to do with hybridization, which is something that we have not yet discussed. If you're very interested, you can look in your textbook tonight and now. If you're willing to wait or are already overwhelmed, please feel free to do so on that topic. More information will come from that as we move forward. I know this was a lot. I know this was a relatively long one. I hope you found it helpful, and I'll see you in class.